Welcome to our talk on understanding tangent lines and how they relate to velocity. This is everything you will need for section 2.1. So the first thing I want you guys to understand is this picture over here is just a simple function, a circle with a couple tangent lines. And if we zoom in and continue to zoom in, and we're paying attention to this spot right here, that's where the line hits the circle, where it's tangent. If you zoom in and keep zooming in, what do you notice happens to the curved line of the circle? It seems to straighten out, and that's really just what's happening when you're looking at a smaller and smaller piece. Think about the Earth. The Earth is round, but when we look at the ground, it's flat because we're looking at a very, very small portion of that entire thing. So that's the first thing I want you guys to understand, is that if you zoom in on any type of curve, whether it's a circle or a parabola or a sine wave or whatever, if you take basically a small enough interval of that curve, which is what's happening. See, when we've zoomed in here, this entire screen is really only looking at maybe the difference between x equals 5 and x equals 5.000001. It's a very, very small interval of that function. So when you zoom in and take a very small interval, you're basically getting a flatness. It becomes straight under really small intervals. Alright, so that's the first thing. The second thing is that we can always approximate the slope of our tangent line by using secant lines. So this blue line here is a tangent line. It's tangent to this point right here, A. And you'll see that the slope of our tangent line is 0.95. And we can move this point around and get all sorts of different slopes. So there it's almost horizontal, so slope is 0. And then we get some negative slopes, right? And then we're back over here to positive slopes. So we can move this all over the place and get different slopes. Let's put it right here at the point 0, and you can see that that's a nice little 45-degree angle, and it actually gives us a perfect slope of -1. Well, we can approximate this slope with our tangent line, with our secant line, by getting it closer and closer. So you can see as B is getting closer to A, look what's happening to the slope of the secant line. It's getting closer and closer to that -1 until we finally get it right there, and then it's undefined, because at this point it's trying to calculate a slope between B and A that are the same points. So that's what's happening there. That's why it's undefined. But you can see that we can get it at really super close, and they're almost identical in both directions, right? We can start over here and we can bring it back and get it really close to -1. Okay, so we can approximate slopes of tangent lines by using slopes of secant lines. The next thing I want you to understand, and these are all still conceptual things, right? We haven't learned any techniques of how to compute things. I just want you to understand the concepts. The next thing would be if we had a function that looked something like this, roughly similar to the one we had before. We can look at a secant line that goes from here to, let's say, here, as giving us the average rate of change of this function between these 2 points. So basically going between these 2 points, right? It's -10.5, right, up to about -1.5. So that's my change in x. My change in y goes from, let's just say it's right there at 0 up to about 3, right? So that's my average rate of change. So as x goes from -10.5 to -1.5, my y value goes from 0 to 3. So secant lines give you an average rate of change. And in fact, we can think of average rate of change as change in y over change in x, which you should recognize as m, our slope. Right? So in this case, our change in y was 3, right? We went up 3, and we went over How far? Well, do the difference between these two, 9, sorry, 1/3. So that's a rate of change, an average rate of change of 1/3. So over this interval, from there to there, the function has an average rate of change of 1/3. You can see that here it's increasing rapidly, less rapidly, right? Kind of not changing at all, and then it's actually coming back down, decreasing. So the average doesn't tell us a lot, whereas the slope of the tangent line, and the tangent line gives us the instantaneous rate of change. It's how fast the function is changing instantaneously, and this is supposed to be touching at that point again, even though I know it looks like it's touching there. So conceptually, that's the other big difference. The secant lines gives us average rate of change. The tangent line gives us instantaneous rate of change. Another technique you guys should learn from this section is how to approximate the slope of a tangent line by using secant lines. So here is a picture of a parabola. This is the formula for the parabola, 4.9x squared, real simple. And here we have the secant line. This is the line going through AB. It's a secant line. I know it's hard to tell, but it is actually a secant line there. If we move B over here, you'll see that it's a secant line, right? It's just connecting two dots on the curve. Okay, over here we have a table I did in Excel really quickly to calculate slopes of this secant line for different points. So we're trying to approximate the slope of the tangent line at the point 5 by looking at the slopes of the secant line. So we start with this point here, as you can see, going through the point 5 and 6.08, close enough. And you can see my slope here is 5.4 and over here 5.39. And as we let B get closer and closer to A, you'll notice that my slope is going down, and over here it's also going down. And you can see from these numbers that it's basically approaching 49. And in fact, if we take B and get closer and closer to A, you'll notice that the slope over there is getting closer and closer to 49 until it pretty much goes from 49 to a little bit less when it jumps the other side. So it looks like it's approaching 49. Now you're probably asking, well, how the heck can I do that on homework? I don't have this fancy GeoGebra stuff. Well, what I mean is you should learn how to just do these by hand or with a calculator, as far as you're just simply calculating a slope between 5 and 6, and then a slope between 5 and 5.5, etc., etc., etc. So remember your formula for slope. Change in y over change in x, and you can calculate all these slopes fairly painlessly and see what happens to the pattern. Over here is just another example with a different function. Now I'm obviously not going to have you do a lot of this on a test because it's very time consuming, but just know that it can be done, right? We can approximate it not only graphically, right, but numerically.